starlight tightens into a thin, unwavering beam. Then, almost imperceptibly, it dims. Not as night falls, not as a cloud passes, but as a world slides in front of its star and makes a clean, silent cut across the light. A shadow crisp at the edges, indifferent to our desire for answers. And inside that shadow, inside the faint change of colors that rides along with it, there's a rumor: methane. This is K2-18b, an exoplanet we cannot touch, cannot see as a disk, cannot sample with a probe. We know it first as geometry, the timing of a transit, the depth of a dip. And then, if we are careful, as chemistry written in missing light. But the title's promise is not comfort. It's a warning with a pulse. Shadow on K2-18b changed again. Methane versus line confusion. What we know, the hook isn't simply that methane might be there. It's that the story has shifted. The signal has changed again, at least in our reading of it. And the difference between discovery and self-deception can be a single misread line. So what does it mean when a signal changes again? It can mean the planet changed. But an exoplanet atmosphere, work that is rarely our first, most honest assumption. More often, it means our picture changed, the way we cleaned the data, the way we modeled the spectrum, the way we decided which molecular fingerprints count as real. It can mean a feature that looked solid now looks conditional, or a feature that looked like methane now looks like something else, or simply the same faint wiggle can wear different names depending on the tools we use to interpret it. The immediate mystery is not philosophical, it's measurable. A methane-like feature, some structure in a spectrum that seems to line up with what methane would do in an exoplanet atmosphere, now sits under suspicion. Because in spectroscopy, molecules don't speak in single, unambiguous words. They speak in overlapping syllables. And sometimes the difference between methane and not methane is not the universe. It's our line list, our assumptions, our resolution, our coverage. A methane versus line confusion. The same like two stories. Here's the tension pair stated plainly: signal versus artifact. A genuine atmospheric signature versus an interpretation error. Planet atmosphere versus a confounder we didn't fully account for. We need to hold two truths in the same frame. First, it is possible to learn about an exoplanet atmosphere from a transit. When a planet crosses its star, a small fraction of starlight filters through the planet's atmospheric edge. If certain wavelengths are absorbed more than others, the transit depth changes with the wavelength. That difference is the raw clue. That is the breath print in the light. Second, that clue is fragile. It's faint. And it lives in a place where many things can imitate each other. A small bump or dip can be a real molecular absorption feature, or it can be a blend of different molecules, or it can be a product of how we corrected the instrument, or it can be a consequence of how we forced the model to choose among possibilities. The exoplanet atmosphere we want to understand is not the only author of the signal. This is why methane of all gases can feel so emotionally charged. Methane is a word that echoes with signs of life. It's a biosignature adjacent word. On Earth, methane can be produced by biology, but on other worlds, methane can also arise through non-biological pathways. And at the distance of an exoplanet, we are not measuring a source. We are trying to infer a presence from a spectral pattern. It is a long leap from methane might fit the data to life. That leap is where false positives live, and we are not making it. In this opening movement, the key question is narrower and more rigorous. What does the data actually support when we say methane, and what could be fooling us? The changed again language matters here because it reminds us this is not a static photograph. It's an evolving inference. In exoplanet spectroscopy, interpretations can shift for reasons that are almost invisible in headlines. New ways of processing the same observations, revised models' better understanding of what counts as contamination. That isn't weakness. It's the method trying to protect itself from a false positive, an evidence moment right now without numbers. The measurement is spectral structure, not a blank line. The exoplanet atmosphere is not featureless in every plausible reading. There is something in the data that invites molecular interpretation, but the identity of that something is contested. That is the entire drama of methane versus line confusion. Line confusion is the confounder with a deceptively simple name. It can mean misidentifying one molecule's absorption as another's because their features overlap. It can mean incomplete lineless molecular databases that may not capture every relevant transition under the temperatures and pressures we're dealing with. It can mean the spectrum's resolution is too coarse, or the wavelength range too limited, so multiple candidates can hide inside the same shape. The data can be real, the feature can be real, and the label can still be wrong. And when the label is wrong, the meaning collapses first. We don't just lose methane. We lose the narrative momentum that turns an exoplanet atmosphere into a possible biosignature. We learn again that nature is not obligated to be unambiguous. So we begin with a discipline. We separate what we know from what we infer, from what we speculate. We know an exoplanet transit produces a measurable change in starlight. We know that spectra can carry molecular information. We know that overlapping molecular features can create line confusion. We infer that a methane-like interpretation is one plausible fit, not a direct sampling of air. We can speculate carefully that if methane were eventually supported by multiple consistent features and ruled cleanly against confounders, it could become part of a larger signs of life conversation. But that speculation sits behind a locked door, and the key is evidence. Because the atmosphere is not the only place where this story can go wrong. If we want to understand why the shadow on K2-18b changed again, we have to go to the place where the whisper becomes a plot. We have to trace the chain from photons to a spectrum to a retrieval without romanticizing it, without stripping it of awe. The awe is real, so is the uncertainty. The shadow continues its quiet passage. The light returns. And we're left with a question that is as technical as it is human. How do we turn that tiny color-dependent dip into an honest statement about an exoplanet atmosphere without being fooled by line confusion, by our own assumptions, by the instrument's quirks? To judge the methane claim, we have to see how the shadow becomes a spectrum step by step and exactly where doubt enters. The first thing you notice is how ordinary the star looks, just a point of light steady to the naked eye. But in the data, it's not steady, it's not simple. It's a storm of photons, a flow of counts and corrections, a tightrope walk across noise. And somewhere inside that flow, a planet's shadow leaves a fingerprint so small, you can almost believe it was never there. This is the part where we earned the phrase, what we know. Because the title isn't just telling us that the shadow on K2-18b changed again. It's hinting that our interpretation can change again too when the path from measurement to meaning runs through machinery calibration and model choices. Methane versus line confusion is not decided by confidence. It's decided by process, by whether the same feature survives each step without being manufactured, distorted, or erased. So here is the key question for this section. What exactly is measured, and what steps can create or destroy a methane-like feature? Start with the simplest statement. During a transit, we measure how much starlight is blocked, not once, but across many wavelengths. That gives a spectrum of transit depths, how big the planet appears in different colors. If the planet's atmosphere absorbs some wavelengths more than others, the planet looks slightly larger at those wavelengths. That is the core observational channel. That is transit spectroscopy in one sentence. But the measurement isn't methane. The measurement is light. An evidence moment. The data arrive as raw detector counts, not as a tidy plot labeled with molecules. Before any discussion of methane, you have to turn those counts into a stable, wavelength calibrated record of how the star's light changed during the transit. And every correction you apply is a choice necessary but consequential. Calibration is where humility becomes technical. You correct for detector behavior, how the sensor responds at different brightness levels, how it drifts over time, how pixels behave when they warm or cool. You correct for background light. You map which detector positions correspond to which wavelengths. You align timestamps so you know exactly when in transit begins and ends. Each step is meant to remove what isn't the planet. But each step can also imprint patterns that look like the planet. This is the first confounder test we name, clearly instrument systematics. Instrument systematics are not vague uncertainty. They are specific ways instruments can fool us thermal stability issues, detector effects, wavelength calibration quirks. They can create gentle slopes, subtle bumps, or small shifts that masquerade as an atmospheric absorption feature. Or they can flatten a real feature into silence. In a case like K2-18b, where the signal is faint and the stakes feel high, systematics are not an afterthought. They are part of the story's plot structure. Signal versus artifact. Now suppose you have a calibrated spectrum transit depth versus wavelength. The next step is where the human urge to name things gets formalized. We build models of an exoplanet atmosphere, different mixtures of gases, different temperatures, different cloud properties, and we ask which models best reproduce the spectrum. This is retrieval. Retrieval is not a single answer generator. It's a method for exploring possibilities. It takes the spectrum and returns probability distributions over atmospheric parameters, gas abundances, temperature structure cloud, /haze behavior, understated assumptions. It does not hand you a trophy labeled methane. It hands you a map of what the data allow and how strongly. And this is where methane versus line confusion starts to sharpen. If a feature lines up with methane, the retrieval may assign methane a non-zero probability. But methane can share spectral neighborhoods with other molecules. Features can overlap. Different combinations can produce similar shapes, especially when data coverage is limited or when clouds mute contrast. So methane can emerge as a plausible fit without being uniquely required. Another evidence moment when multiple models fit the same spectrum comparably. Well, that's not failure, it's a result. It's the data telling us I cannot uniquely identify this molecule yet. This is also where the phrase changed, again, can gain a more precise meaning. A spectrum can appear to change because a new calibration step handles a systematic differently. A methane-like feature can rise or fade depending on how the pipeline treated drift. A retrieval can shift its preference depending on model assumptions, what chemistry is allowed, what temperature profile is permitted, how clouds are parameterized. These aren't cosmetic differences. They can move the probability mass from methane likely to methane optional, or from feature to noise-like. We have to say that cleanly because audiences deserve it. The inference chain is not a weakness. It's the only honest way to translate distant starlight into statements about an exoplanet atmosphere. But it does mean the conclusion is conditional. It is tied to explicit assumptions and to the quality of calibration. So how do we keep ourselves from fooling ourselves? We look for redundancy in stress tests. We ask whether independent pipelines, different calibration approaches recover the same spectral structure. We test whether the methods can inject a fake signal and recover it, or remove a real one and notice its absence. We check whether the feature persists across different segments of the observation, across different processing choices. We look for internal consistency. Does the methane interpretation predict additional features elsewhere in the spectrum? Or is it supported by only one ambiguous bump? And we keep the honesty tags close. We can measure wavelength-dependent transit depths. This is the raw exoplanet spectroscopy channel. Calibration is essential, and instrument systematics can mimic or mute small features. Retrieval translates spectra into probability distributions over atmospheric possibilities. Methane can be plausible without being unique. The phrase "changed again" can reflect changes in reduction and modeling, not necessarily changes in the planet. At this point, we've answered the key question in the only way that respects the data. Methane is not a direct detection in the way a lab measurement is. It is an inference drawn from a calibrated starlight, filtered through retrieval, and model assumptions tested against systematics. And the moment you accept that the title's tension becomes less sensational and more profound. What we know is not a headline. It's a chain of custody, but there's still a missing character in the story. Because even if the instrument were perfect, even if calibration were flawless, even if retrieval were mathematically immaculate, there is a foreground that can write its own false spectrum. A living, textured surface behind the planet's path, the star. And if we want to understand why the shadow on K2-18b seemed to change again, and whether methane is signal or line confusion, we have to turn our attention from the planet's edge to the star it crosses and ask whether the star has been the hidden author all along. The star's light looks clean when it reaches us. A single point, a steady glow. But up close, if we could close the distance, it wouldn't look like a blank bulb. It would look like a surface, a living texture. Bright patches, dark patches, regions that simmer and shift. And the planet doesn't transit the star. It transits a particular chord across that surface. That is the change of perspective. In the title, the shadow on K2-18b changed again. In the last section, we traced how calibration and retrieval can shift a spectrum. But there's another way a signal can change again without the planet changing at all. The star can alter the apparent spectrum that we attribute to the exoplanet atmosphere. Methane versus line confusion can become something even more unsettling: planet atmosphere versus contamination. Signal versus a false positive written by the light source itself. So here's the key question now. Could the methane-like feature be real and still not belong to the planet? The answer begins with the simple, uncomfortable fact: stars are not uniform backdrops. Stellar surfaces can have spots cooler, darker regions, and faculae brighter regions. Those features have different colors, different spectra. And when a planet transits, it blocks a small piece of that surface. If the blocked region is not representative of the star as a whole, the before versus during transit comparison can pick up the star's patchiness as if it were the planet's atmosphere. This is stellar contamination, not as a vague worry, but as a specific mechanism for false positives in exoplanet spectroscopy. An evidence moment stated without numbers. The transit spectrum is a difference measurement. It depends on what the star looked like out of transit compared to in transit. If the star's surface is heterogeneous, the difference can be wavelength dependent, even if the planet had no atmosphere at all. That wavelength dependence is exactly the kind of structure we chase when we infer atmospheric gases. This is the tension pair in plain language planet atmosphere versus star contamination, and it gets sharper when we remember the title thread, the signal changed again. If the star's active regions evolve between observations, or if the planet crosses different stellar latitudes, the apparent spectral signature can shift. It can look like methane one time and look ambiguous the next. Not because methane came and went, but because the star's surface pattern changed the baseline we subtracted. This is also where time enters as a confounder. Not time as cosmic grandeur, time as sampling. If you have only a few transits, you are taking a small number of snapshots of a dynamic scene. The star may not be in the same state each time. The transit cord may not probe the same mixture of stellar features. A spectrum that looks stable in one dataset can look different when you add another. Changed again can be a symptom of limited sampling as much as it is a sign of a new discovery. So we name the confounders explicitly as the outline demands. First, stellar contamination spots and faculae chromatic effects heterogeneity across the surface. Second, time variability versus sampling few transit short baselines and the risk that we mistake when we looked for what the planet is. And now, methane versus line confusion gains a third dimension. Even if methane's spectral pattern overlaps with other molecules, the star can introduce its own overlapping patterns. You can do a careful retrieval and still be fitting a mixture of planet plus star effects. The retrieval might assign methane a role because methane is one way to explain the shape, but the shape could be partly or in extreme cases largely stellar in origin. For viewers, the plain language translation is this: we're trying to hear a whisper from the planet's atmosphere while the star is singing behind it. Sometimes the star's voice changes, and the whisper seems to change with it. That doesn't mean the whisper is fake. It means the microphone is picking up the room. This is where the seriousness belongs. Not in claiming certainty, in designing the questions that can separate these effects. What would increase confidence that a methane-like feature belongs to K2-18b's atmosphere rather than the star's? We look for consistency across conditions that should not matter if the signal is planetary. We ask whether similar spectral structure appears when the star's activity is different, whether the feature tracks stellar variability or remains steady despite it. We look for patterns that are difficult for stellar heterogeneity to mimic across broader wavelength coverage. We search for internal coherence. If methane is invoked, does the spectrum show multiple hints consistent with methane's broader fingerprint, rather than a single ambiguous feature that can be swapped for something else? We keep the honesty tags close, because this is exactly where narrative temptation can outrun evidence. Stellar surfaces are heterogeneous. Spots and faculae can imprint wavelength-dependent effects. Transit spectroscopy is a differential measurement sensitive to the heterogeneity. Apparent molecular structure can arise from unmodeled stellar contamination, especially when sampling is limited. If future observations show the same structure across different stellar activity states and expanded wavelengths, confidence shifts toward a planetary atmosphere origin. And we tie back to the title directly because it's not decoration, it's accountability. When we say the shadow on K2-18b changed again, we're not just describing drama. We're describing a system where the planet, the star, the instrument, and our models all contribute to what we think we see. The methane headline lives or dies on whether the signal survives these tests. What we know is that the star can produce false positives. What we infer is that it might be part of this story. Now we arrive at a harder, quieter place. Because once you accept that multiple worlds can fit the same faint data, planetary gases, overlapping lines, stellar contamination, You're forced into an uncomfortable kind of honesty, the kind where the best conclusion is not an answer, but a boundary around what an answer can be. And that boundary is the next section. We're going to stop chasing labels for a moment. Methane, not methane, and ask a more disciplined question. Given everything that can fool us, what can we honestly conclude today about methane on K2-18b without overstepping the evidence? The plot is still the same: starlight, a shadow, a spectrum, but the feeling changes here. The room goes quieter. The imagination steps back, because this is the moment where we make a promise to the audience. We will not pretend that a thin line on a graph is a verdict. A spectrum is not a confession, it is a clue, and the title demands this checkpoint. Shadow on K2-18b. Changed, again methane versus line confusion. What we know. If the signal changed again in our interpretation, then the only honest response is to tighten our language, to separate what the data show from what our models prefer, to say clearly what we can and cannot conclude about an exoplanet atmosphere right now without turning uncertainty into a nuisance we hide. So this section's key question is simple and strict. Under today's uncertainties, what is the strongest statement we can make that won't collapse tomorrow? First, the ground truth. What we know is that the measurements contain spectral structure, something other than a perfectly flat, featureless line, inviting molecular interpretation. That alone matters. It says the data are not empty. It says there is an exoplanet atmosphere story to attempt, even if it is incomplete. It does not by itself tell us the molecule. It tells us the data have shape. An evidence moment, the existence of structure is the evidence. The identity is the argument. The structure is the part we can point to. The label is where interpretation begins. Now the contested word methane, the most honest framing, consistent with the outline, is not methane is detected. It is methane is a plausible explanation in some models of the spectrum, but it is not uniquely required because alternative explanations can fit. The space of plausible atmospheres is still wide. Clouds can blur features. Temperature and composition can trade places in the fit. Overlapping molecular lines can create confusion. The star can contaminate the measurement. And the retrieval itself is a set of conditional statements built on model assumptions. This is where we state the tension pair plainly: detection versus interpretation. We may detect structure, but interpretation is where uncertainty lives. So we ask, why does the interpretation keep feeling like it changed again? Because retrieval is not a single lock with a single key. Retrieval is a landscape of competing explanations, constrained by prior choices we make about what atmospheres are allowed to be and how. Do we assume chemical equilibrium or allow disequilibrium? Do we treat the atmosphere as one-dimensional uniform or acknowledge three-dimensional complexity? How do we parameterize clouds and hazes? What temperature profile do we allow? These are not aesthetic choices. They shape the probability distribution we call a conclusion. And now we name the confounder required for this checkpoint explicitly retrieval priors/model assumptions. A retrieval can favor methane more strongly if the priors or the allowed chemistry make methane easy to invoke. Another retrieval, equally competent, might find methane less necessary if it allows different mixtures or treats clouds differently. That doesn't mean one team is honest and the other isn't. It means the data do not yet uniquely constrain the problem. The best fit is conditional, an evidence moment without inventing specifics. When the same spectrum supports multiple plausible solutions, the correct scientific move is not to pick the most exciting one. It is to state the ambiguity and define what additional data would break it. That is not hedging, that is rigor. So what is the best current conclusion we can responsibly stand on? Here it is. In the outline's own logic, the atmosphere is not featureless, yet the identity and abundance of methane remain uncertain. Methane is plausible in some fits, but alternatives can fit due to degeneracy clouds, hazes, temperature structure composition overlaps, plus the uncertainties from calibration and stellar contamination we have already named. The strongest statement that is unlikely to collapse tomorrow is not a molecule claim. It is a constraint claim. The data meaningfully restrict the space of possible atmospheric stories, but do not yet force a unique one. And we must explicitly touch the title's core tension. Again, methane versus line confusion. Line confusion is not merely a technical footnote. It is a reminder that nature's alphabet can be reused. Different molecules can leave similar marks, and incomplete or imperfect line knowledge can shift the interpretation. Even if the data are stable, our labeling can change again as line lists improve, or as we notice overlaps we previously ignored. That is one of the reasons we treat methane as plausible, not final. Here's how we keep the emotional stakes honest for a viewer who cares about signs of life. Methane is a molecule that can sit near the doorway of biosignature conversation. But a single molecule, especially one vulnerable to false positives and overlapping lines, cannot be treated as a sign of life on its own. A biosignature claim would demand more multiple consistent features, chemical context, and aggressive testing against confounders. The outline does not give us that, and we do not pretend it does. So the checkpoint is not a disappointment. It is a map. We've done the difficult thing. We've held the awe and the doubt together. We've admitted that the universe is readable, but only with conditional grammar. We've refused to turn a probability distribution into a headline. And now the next step is practical, not philosophical. If the conclusion is conditional, then we must name exactly what measurable uncertainty keeps it conditional, and what kind of future data could turn changed again into converged. We have to go straight at the problem that keeps methane and line confusion tangled. In the next section, we lean into limitations not to diminish the story, but to sharpen it until one measurable unknown stands at the center waiting for the next clean test. The spectrum hangs in the dark like a thin thread, not a banner, not a proclamation, just a fragile trace light that left a star skim past an exoplanet atmosphere and reached us altered by everything along the way. In this kind of work, the difference between discovery and illusion can be the smallest bend in that thread. We return to the title's promise one last time, because it's the spine of credibility. The shadow on K2-18b changed again, and the fight is methane versus line confusion. What we know, what we infer, what we still cannot name. If the signal can change again in our interpretation, then this final movement has to be limitation heavy, not as an apology, as the only honest way to stay close to the evidence. The key question now is practical and sharp. What exact observation would most cleanly separate methane from confounders on K2-18b? To answer, we have to admit how many ways nature can hide the truth. First, the planet's own atmosphere can obscure itself. Clouds and hazes don't just add mystery for dramatic effect. They flatten, they smear, they mute. In transmission, spectroscopy, a high cloud deck can make a rich atmosphere look nearly featureless, or it can soften the very features we want to interpret. That creates degeneracy. Different combinations of gases and clouds can produce similar-looking spectra. The atmosphere can be real and still be hard to read. This is one of our explicit confounders, cloud/hazes degeneracy, an evidence moment supported by the outline's logic. If clouds can mute features, then an apparent methane bump might be the surviving edge of a broader pattern we can't fully see, or it might be a shape created by the way clouds reshape the spectrum, making one molecule impersonate another. The data can be honest, the interpretation can still be wrong. Second molecules can impersonate each other because their signatures overlap. This is the title's central antagonist line. Mice identification / incomplete line-less line confusion. Spectral features are not neatly separated stamps. They are overlapping fingerprints pressed onto the same piece of paper. If line lists are incomplete at the temperatures and pressures relevant to this atmosphere, or if the spectrum is limited in resolution or wavelength coverage, methane can be plausible without being uniquely identified. Here the tension pair is model fit versus reality. A model can fit beautifully and still be fitting the wrong molecule because several candidates can occupy the same spectral space. That's not a failure of imagination. It's a consequence of physics and limited information. Third, the star can still be a hidden author. Even after careful calibration and retrieval, stellar contamination spots, foculi heterogeneity can imprint chromatic patterns into the transit signal. We discussed it in the change of perspective, and it belongs here again because it is one of the most dangerous false positive pathways. If the star's surface changes between observations, the spectrum can change again even if the planet's atmosphere is stable. So the name confounders we must hold together are clear: clouds / hazes, degeneracy line, mice identification / incomplete line lists, stellar contamination. All three can push methane toward the front of the story or pull it away without ever touching the truth of what gases are actually present. Now, the key question asks for the one measurement that could settle it, and we have to answer within the outline's constraints: no invented specifics, no new claims. So we stay with the measurable path the outline provides. The way out is not a single heroic data point. It's a specific kind of constraint, broader wavelength coverage, and repeated transits that test for a consistent multi-feature pattern. If methane is truly present at meaningful abundance in K2-18b's atmosphere, it should not announce itself in only one ambiguous place. It should leave a coherent set of hints across separated wavelength features that rise and fall together in the way methane physics demands. That becomes our cleanest discriminant. Not is there a bump, but does the same molecule explain multiple features across a wider span of the spectrum consistently over time? An evidence moment repetition is not redundancy for comfort. In exoplanet spectroscopy, repetition is a diagnostic. If the same structure appears across multiple transits, despite changes in stellar activity state, that pushes against the idea that we're seeing a stellar false positive. If the structure shifts with the star, that points toward contamination. Either way, more well-chosen data doesn't just add confidence, it changes which explanations remain viable. And because line confusion is at the heart of the title, we name the specific logic that breaks confusion, separate the overlaps. Broader wavelength coverage can reveal whether methane's implied pattern is supported elsewhere, or whether another molecule or clouds better accounts for the full shape. It is the difference between recognizing a person by one blurry feature versus recognizing them by a full face. Now we give the audience the final honesty tags woven into the meaning without preaching. Clouds and hazes can distort or mute spectral features, creating degeneracy in atmospheric interpretation. Line confusion, misidentification, or incomplete line lists can cause methane-like features to be mislabeled. Stellar contamination can imprint false structure into transit spectra. Broader wavelength coverage and repeated observations can break degeneracies by demanding a consistent multi-feature molecular pattern and by bounding stellar effects. If future spectra show a robust methane consistent pattern across wavelengths and time, and if stellar contamination is tightly constrained, methane becomes much harder to dismiss, but still not a life claim. And we make the caution explicit because signs of life is always hovering at the edge of this conversation. Methane alone, especially methane inferred under line confusion and cloud degeneracy, cannot be treated as a biosignature. Not yet. Not in this case as outlined. Any signs of life framing must remain conditional and disciplined, because false positives are not rare in this regime. They are expected possibilities. So what do we leave the viewer with? Not a verdict, a measurable unknown. Here it is named as the episode's final hinge: methane abundance versus line confusion under cloud/haze opacity. Is the feature truly methane at what level, and how much of what we see is shaped by clouds' overlapping lines or stellar contamination? That unknown is not philosophical. It is measurable. It is the reason the shadow can seem to change again. And we end with what future data would resolve without expanding beyond the outline: broader wavelength coverage, repeated transits, and stronger constraints on stellar heterogeneity. So the same story must hold across multiple tests, or it must give way. The star remains a point. The planet remains a shadow. The spectrum remains a thin thread of altered light. Somewhere in that thread, a world is trying to tell us what its atmosphere is made of. Our job is not to force the message to be methane. Our job is to learn when the message stops changing, because we finally learned how to read it.